guess I didn't. Blow this up. All right, so here is HCN. This is just a generic setup for simultaneous method where C is the initial concentration for HCN. I had it at what, 10 to the minus 6 molar, 10 to the minus 7 molar. The example problem we looked at the other day, and so you put that here for the initial concentration. And then we assume that none of it is hydrolyzed yet. And so we're going to get HCN at equilibrium and cyanide at equilibrium. And then the hydronium, we've got to figure out what the hydronium is going to be. Since this is a simultaneous setup, set it up the same. Am I doing mass balance here? Yeah, this is, these are some other equations you can generate. This is mass balance. And so the concentration C here, the initial concentration, is going to be basically the HCN that remains unreacted plus the cyanide. And so this total initial concentration here is going to end up in 2 species at equilibrium. It's going to end up here and here. So this is another equation we can generate. What we try to do is we try to generate as many equations as possible here and then solve whichever ones look good simultaneously as a system of equations. And so the initial concentration here, sometimes I label it differently. I just call it HCNI. I should have done that. And this is HCNE and CN minus E. So all that breaks up into these 2 species. And then the total hydronium concentration, this is called mass balance. These are mass balance equations. The total hydronium ion concentration is going to equal, okay, the total hydronium concentration is going to equal, well, this is called charge balance. And the total hydronium, we only have one positively charged species in all these equations. And the total positive charge has to equal the negative charge total. And so this equation, what is this? Did I label this? C and D. Did I get this in right order? Where's my A and B? Okay, so these are the equations we have so far. Equation A, which is just the equilibrium constant expression. Equation B, which is Kw. This is the other equilibrium we have to include on top of that, because for an acid we have 2 hydronium producers, HCN and water. These 2 hydronium producers are going to be tied together because the total hydronium has to be the same in both. So we have our 2 normal equations here. And then I'm going to add a mass balance equation. This is a mass balance equation here where the initial HCN is going to end up in these 2 species here, HCN and cyanide, and hydronium too, but the hydronium is now mixed up with the hydronium from water, so I can't include hydronium, so cyanide is going to serve that purpose here. This is just molarity. And then this is charge balance, where the total positive charge is equal to the total negative charge. Okay, and then just put it together. And so we could solve for the cyanide concentration here and come up with this equation, which is, this would be the mole fraction of cyanide. And the mole fraction of cyanide is the cyanide concentration over the total. And so the mole fraction of cyanide would be that over the total here. We have the mole fraction, that's chi cyanide, and then the total molarity here, and this is going to equal C, and then we can generate more equations here, and then we can solve this system of equations here. So this is what you could do. This is one example of solving this here, mathematically. Did I just do math? It's been a while since I wrote this up, but here's the math. It's just a cubic here. A cubic, you could just use your calculator. Anything higher than a cubic, I asked you to solve by hand. And so on the exam, 16, we had a fourth order polynomial I wanted you to solve by hand. And so if you solved it using your calculator, that wasn't supposed to be. And you go, well, what's the big deal, because calculators can do it? The big deal is that a lot of equations in science are difficult to solve, even with a computer. You have to make approximations. And we do that all the time, especially in quantum mechanics. We make approximations. And so you can't use an equation solver in a programmable calculator for that particular. You weren't supposed to use it, so I'm going to deduct it some points. What was the concentration I used for HCN initial? So I got to see C. I think this is 1 times 10 to the minus 5 molar. So this problem was different. This is a homework problem in the book. The pH comes out to 6.8956, almost neutral. All right, that's one method. Another method of solving this is what we did earlier. Kind of had it set up. The book goes through it, but so I just wanted to show a mass and charge balance example, and this is the type of stuff you do in mass and charge balance here. The important thing is to recognize when you're in that loop, the death loop, where you're just going in circles. Okay, so that simultaneous. Again, there are 2 ways to solve those. And there's some hints for solving it the first way we set it up without generating all those mass and charge balance equations. Okay. The 2 ice tables. I have it worked out with the other way too. I guess I didn't. I'll have to dig that up and I'll show it to you later. All right, now what we want to do is hopefully we don't have to use simultaneous, Hopefully stepwise works. So that we don't have to go through that. But if stepwise doesn't work, then all you have to do is set it up and show that it is simultaneous. You don't have to actually solve it to get full credit for it. So let's take a look at some other examples. We're going to look at polyprotic species and bases. So actually, sometimes we ignore the KW. And so if we go back to the amide, what was it, sodium amide example here, it depends on the concentration of amide here. So we know that amide is a strong base. The way I treat this is it's not sodium amide. This is a sodium salt. Sodium salts are soluble. And so what I say, it's a soluble salt. Soluble salts ionize completely, so we get sodium and amide. K for this is very large because soluble salts are strong electrolytes. And then we have amide here. Amide is a strong base. And we end up with ammonia and water. And we know that K is like 1 times 10 to the 42. It's huge for this. Or not ammonia and water. It ends up with ammonia and what? Ammonia and hydroxide. So if we had something like initial 0.100 molar here, and 0 molar here, 0 molar here, then what we're going to get is we're going to get something like 0.099999 molar hydroxide. If I'm only interested in pH, what would I do? If I'm only interested in pH, then I would probably stop here. But there's another source of hydroxide. What is the other source of hydroxide? This is Kb. The other source of hydroxide is water. And so we're going to get hydronium and hydroxide here. Actually, I think I forgot to do the last problem we were looking at, but we'll just continue with this. Okay, if I'm only interested in pH, well, a couple of things. Will step 2 here perturb step 1? Well, what's the most hydroxide we're going to generate from Kw? The most hydroxide we can possibly generate is 10 to the minus 7, but we're probably going to generate a heck of a lot less than 10 to the minus 7 because we have so much hydroxide. We have 10 to the minus 2 or 10 to the minus 1 hydroxide here. Already, this is like 0.1, so it's like 10 to the minus 1. And so if we already have a lot of hydroxide in there, we don't expect it much additional. And so if we get like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10 hydroxide, will that impact this? No. And the other thing is, this is one way. I mean, when the Kb is very large like this, we don't really worry too much about the Le Chatelier's perturbation. And so it depends. If I want hydronium, then I'd have to do this next step. Okay, so there are different things. I could have stopped here, like pH. If I want the pH is the negative log of the hydronium ion concentration. Okay, so there are two ways we could get that. I could go on to this step and determine my equilibrium hydronium concentration here and plug that in here. That will be my equilibrium. Alternatively, I could skip the Kw step. If I skip the Kw step, then what I'm going to do is I'm going to assume that water is negligible contributor. And if water is a negligible contributor, then I can calculate the pOH. The pOH is going to equal the negative log of the hydroxide concentration here. And this should be at equilibrium, but we're assuming that, again, assume Kw is negligible. Here, hydronium is going to be significant because we start off at 0. Here, we're starting off at 0.09999, and then we're going to get the hydroxide at equilibrium. And we expect it to be a very small addition here. And so if we assume that Kw is negligible, then what we do next is we say that the pH is just equal to pKw, which is 14.00, minus the pOH. So they're interrelated. And so those are two ways of determining the pH of the solution. If this were me, I wouldn't have done Kw. I would have just done Kb, assumed that I'm not going to get much, and then calculate the pOH and then determine the pH from that. All right, so here we don't have to worry about simultaneous. Okay, next we're going to look at polyprotic acids and polybasic bases. Polyprotic acids and polybasic bases. So if I have a polyprotic acid, let's say something like H3PO4, what happens with this is all three hydrogens don't break off at the same time. What happens is there'll be a collision, and we'll remove the most acidic hydrogen first. The most acidic hydrogen will just be the first hydrogen ion on that, and we're going to form dihydrogen phosphate. Now, this is going to be Ka of H3PO4, which is equal to Ka1 of H3PO4. So we're going to go ahead and do this. We're going to do at an initial concentration of 3.00 molar. This is fairly high, you know, and having a high concentration here means we're going to deviate from ideal behavior a bit. It's not really high in the context of acids and bases, and chemical reactions. It's just high in the context of ideal versus real behavior. These, but the reason I'm leaving it high here is because if I go with 3.00 molar, then the simplifying assumption works. If I make this concentration low, then I'm going to have to solve the quadratic for each step. And so this is why the book chooses 3 molar. Although it's a bit odd, they choose it so that they don't have to do the quadratic. And so at equilibrium, I'm going to get 3.00 minus x, and x molar. And you should know the simplifying assumption. You can say, well, the simplifying assumption don't really need to know that, because if you could just do the quadratic, then you don't have to make that assumption. But it can really speed things up. And so can you take a look, where's phosphoric acid? Well, phosphoric acid is on the higher end of the weak acids. Do you see it? There. We're going to use the value on that chart there, which is 7.5 times 10 to the minus 3, which means it's one of the stronger of the weak acids. You know, if you look at the strongest weak acid, what is it up there? Well, it's like 5.9 times 10 to the minus 2. 5.9. So when you're looking at the 10 to the minus 2, 10 to the minus 3 range, we're looking at the stronger weak acids versus the weak, really weak acids. And the really weak acids are going to have a very small value. You know, if you look at water, water is 10 to the minus 14. Kw is the same as Ka and Kb. I'll write that here. Kw for water is the same because water plus water makes hydronium, that's Ka, and water plus water makes hydroxide, that's Kb. So Kw for water is the Ka for water and the Kb for water. It's the same thing. And so that's why you see when you look at the Ka value for water, it's 10 to the minus 14, which is the same as Kw. All right, this is 7.5 times 10 to the minus 3. This is just going to equal the hydronium concentration at equilibrium times the dihydrogen phosphate concentration divided by the phosphoric acid concentration. And this is just going to be equal to x squared over 3.00 minus x. And then we're just going to use the simplifying assumption here and hope it works. So the simplifying assumption is x is going to be much smaller than 3, so we're going to get x squared over just 3.00. And therefore x is equal to, let's calculate that out here, 3 times 7.5. Now I'm using the Ka value from this chart here. The Ka value from this chart is not the same as our book. Our book has more current values. That chart has old values. They don't update the values there. This one's going to be close, you know, but I know it's a little different than our book. We'll just use it. 7.5 times 10 to the minus 3 times 3. And then we'll take the square root of that. 0.150 0.150 divided by 3 times 100. And lo and behold, do you know what percent change it is? It's a 5.0% change. A 5.00% change is right on our border. So if I went 2.9, it wouldn't have been good. I could have gone higher. 4 would have been better, right? And so this is why that concentration was chosen again. And so it's 0.15. Okay, so this is going to be 3 minus 0.5 is going to give me 2.85 molar here. And what we say is we have 5% ionization. Now, the percent ionization of phosphoric acid depends on the initial concentration. It's not a fixed number. So the percent ionization actually increases as the concentration decreases. So as the initial concentration of phosphoric acid decreases, you could prove this by calculation. If we have decreasing initial, we're going to have increasing percent ionization. Or as the initial concentration increases, then we have decreasing percent ionization. And so it's not a fixed number. In this particular case, it's 5% ionized here. We're assuming that it would be better to use a quadratic. So if you have a quadratic solver, you get a more accurate answer. And at 5%, it's pushing it. So I would have used the quadratic. But in an effort to save time, we're going to skip the quadratic. And then this is going to be 0.15. See how many sig figs? 2 molar, and then 0.15 molar. All right, now what happens is once we've completely stripped off the first proton, then the second proton will be the next most acidic. So we take the strongest acid, which is going to be H2PO4 minus, plus the strongest base, which is going to be H2O liquid. And this is going to give us, this is an equilibrium, hydronium plus monohydrogen phosphate, HPO4, 2 minus. And what we're going to do is we're going to carry down the concentrations from step 1. So this is going to go down here. This is going to be my initial concentration here. And so I'm going to start off with 0.15 molar from step 1. H2O is a pure liquid. Hydronium, I'm going to start off with 0.15 molar. And I'm going to assume that the dihydrogen phosphate hasn't hydrolyzed yet, so this is going to be 0 molar here. Okay, then there's going to be the change, again, which is minus X, plus X, plus X. And water is pure liquid. So we're going to have 0.15 minus X molar, 0.15 plus X molar, and X molar here. And so this is called Ka dihydrogen phosphate. Ka dihydrogen phosphate is equal to Ka2, step 2 of the phosphoric acid hydrolysis. So they're the same thing. And then we could look this up. If we go to dihydrogen phosphate, it says it's 6.23 times 10 to the minus, what's that, 6? Can't see it from this angle. It's on the right side, about 3/4 of the way up. Do you see that? So 6.23 times 10 to the minus 8. All right, thank you. This is good. What we want in stepwise is this. Do you see step 2 is 5 orders of magnitude smaller? So we're at 10 to the minus 3. That's going to yield the most hydronium. But when we go to 10 to the minus 8, do we expect much additional hydronium? We don't expect much additional hydronium. So this is very good for stepwise. Now, if step 1 were 10 to the minus 3 and step 2 were 10 to the minus 3, then we have a problem. It's most likely going to be stepwise because both of these are going to generate significant quantities of hydronium, and both of them are going to perturb one another. Even 10 to the minus 3 to 10 to the minus 4, it's pushing it there because 10 to the minus 4, this is a factor of 10 smaller roughly. It depends on the numbers, the coefficients. But you see, if we have 10 to the minus 5 drop, then stepwise is looking good. And so I wouldn't really worry too much at this point. And so this is just going to equal the hydronium concentration times the monohydrogen phosphate concentration divided by the dihydrogen phosphate concentration. And so this will equal 0.15 plus x times x over 0.15 minus x. Now, interesting thing happens here when we use a simplifying assumption. We're going to go ahead and use the SA here, which is x is much smaller than 0.5. Well, if x is much smaller than 0.5, then we end up with 0.15 on the top and 0.15 on the bottom times x, and these cancel out. And so there's no math here. X is just equal to 6.23 times 10 to the minus 8. And then calculating the percent change, we'll do the x over 0.15 and see what that comes out to. I'm just not writing it down just to save some time. But on a test, you should write everything down. I need to see your work. This is really good. It's if I did the calculation correctly, 4 zeros in the 4%. It's quite small. So here, I think, even if I use the quadratic equation, it would make no difference. Whereas in step 1, I would have preferred to use the quadratic because at 5%, that's at the limit. And so I probably would have done the quadratic here, skipped the quadratic here, or I would have picked 6 molar or something like that. If I picked 6 molar phosphoric acid or something even higher, then the percent change would be smaller. All right, so going back to this, I have 0.15 minus x. So that's going to be 0.15. Let's see what color I used here. Blue, I'll go black. And x is going to be 10 to the minus 8, so I need 7 zeros after the decimal. 1, 2, 3, 4, 5, 6, 7, and then a 6, 2, 3. So this is going to give me 0.149999. 1, 2, 3, 4, 5. 5 nines. And then 377 molar. And then this is just going to be equal to 0.15, and then I'll need 5 zeros. 1, 2, 3, 4, 5, and then a 623 molar. And then my x is just going to be 6.23 times 10 to the minus 8 molar. All right. And so what we should do after each step is we should double check our equilibrium concentrations here. I forgot to do that here. So let me go ahead and double check it by plugging those back in. So this is going to be 0.15 squared divided by 2.85. And what does that give us here? And 1.5 squared divided by 2.85. 7.89. Oh, that's off. 7.89 times 10 to the minus 3. You look at this number and you compare it to, it should be 7.5. Is that acceptable? It doesn't look so great to me. It looks pretty far off. And this is bigger than rounding, I think. Did I even round? I don't think I rounded this. Let me double check the calculation to make sure I didn't make an error. It would be 3 times 7.5 times 10 to the minus 3. I'm recalculating x equals, and then take the square root of that, equals. Yeah, I didn't round it at all. It's 0.15. But it's off. Do you see it's off? I don't really like how far off it is. I think it should be closer. And so, you know, although you're allowed this here, what I'm going to do is, since this is right at the limit here, I'm just going to alternately use the quadratic. So I'll get this into quadratic form. This is just going to be x squared minus 7 point, actually, I'm not going to write scientific notation here. I'm just going to write it in decimal form. X squared minus 0.0075 x, and then 3 times 0.0075. That should be easy, but just do 0.0225 plus, actually, what would that be? Minus? No. Wait, this should be plus here. This is going to be minus here. Oh, 225 is equal to 0. All right, then I'll go to the quadratic solver. This is minus 0.0075, and this is plus 0.0225. We're going to calculate it. Here. Oops, I must have gotten the signs wrong because I have an imaginary number here. So let me check my math. So it's x squared plus 0.0075 minus 0.0225. I'm sorry? Oh, okay. Let me try that. Oh, yeah, you're right. It's minus 0.025. Let me calculate it. Thanks. All right, using the simplifying assumption, we got 0.15, but here we got 0.146297. So let's try that. Actually, let me leave that up so I can write it. So now I get an x of 0.146. I'm going to carry all the digits because I just want to see how it rounds. So now I'm going to get 0.146297 squared divided by 3 minus x. So let's see what that comes out to. So 0.146297 squared, 0.146297 squared divided by 3 minus 0.146297. Okay, now this is looking good. This is 7.5000 times 10 to the minus 3. So you can see that what happens when we use the simplifying assumption at the limit, our answer is going to be an error. And that's going to lead to a K value that's off. 7.9 versus 7.5. 7.9 versus 7.5 is a significant error. And so, anyway, that's what I would have done had this been myself. But in this case, this percent change is so small, I wouldn't even bother doing the quadratic for step 2. And nonetheless, I mean, 0.146 versus 0.15, it seems close enough, right? But I mean, it rounds, but it leads to a difference. Okay, so anyway, if I'm interested in pH, and I looked at the numbers here, did step 2 really change my pH much at all? So if the question is just asking for pH, I would have just done step 1. I wouldn't have bothered with step 2 because I would have looked, oh, that's 10 to the minus 8. This is 10 to the minus 5. It's 3 orders of magnitude difference. I'm not going to expect much because of the common ion effect. The common ion effect is I have a lot of hydronium here to begin with. I don't need to add much X to get this ratio correct. That's the common ion effect. And so the main reason is I wouldn't have looked at step 2 because number 1, the K value is very small. Number 2, I already have a lot of product there to begin with. Hydronium. If I'm asking for the solution inventory, then I have to do it. I have to do all the steps, including KW. So if we're going to do this completely, okay, then we're going to continue on with this. Okay, so that was step, what am I doing here? This is step 2. So I did step 1. Now I'm doing step 2. Okay, and if I'm interested in the inventory, I'm going to go to step 3 because this is a triprotic acid. And so finally the last hydronium can break off, which is the monohydrogen phosphate plus H2O liquid. This is going to go to hydronium plus phosphate. This is step 3. And so my initial here, I'm just going to carry it down from the previous steps. So the initial monohydrogen phosphate is going to be 6.23. 6.23 times 10 to the minus 8 molar. Water is pure liquid. And the initial hydronium, I'm going to carry down from step 2, is going to be this, which is going to be 0.15. I'm just going to use the value from the simplifying assumption. I know I can't have as much confidence in this value, but for the purposes of this problem, it's enough. And the phosphate, we're going to assume nothing has hydrolyzed yet. And so the change is going to be minus X, plus X, plus X. And so at equilibrium, I'm going to have 6.23 times 10 to the minus 8 minus X. And then 0.15000 627 plus X, and then X. I'm carrying all these digits on hydronium because I want to see how much additional hydronium I get from each step. So from step 1, I got 0.15. From step 2, I got this 627. And then let's see from step 3 how much more I get. And so the Ka is going to equal the hydronium concentration times the phosphate ion concentration divided by the monohydrogen phosphate concentration. And that's going to equal this 0.15 ... plus X times X divided by 6.23 times 10 to the minus 8 minus X. Now, we have a choice here. This is advanced simplifying assumption. Is there such thing as advanced simplifying assumption? I suppose there is such thing as advanced simplifying assumption, because the advanced simplifying assumption would say this. Okay, I could say X is smaller than 0.15. can just use that as my simplifying assumption. This might not be so bad because Ka, what is Ka value here for monohydrogen phosphate? What does it say? 2.2 times 10 to the minus? What was it? 18? 13? 2.2 times 10 to the minus 13. What do you think of that number? That number tells me that monohydrogen phosphate is a little bit more acidic than water. Just a little. It's not very acidic. So, I mean, this is equal to 2.2 times 10 to the minus 13 according to our chart. The book's chart is a little bit different, again, because the book's numbers have been more recently updated. All right, let me close this. Forgot to save this. Well, my Word has crashed, so I'm going to switch to Excel here. Yeah. All right. Somebody tell me the numbers that we had. Well, anyway, this is Ka for monohydrogen phosphate, which is equal to Ka3 for phosphoric acid, which is equal to 2.2 times 10 to the minus 13, which is really small. And so the hydronium ion concentration we had from before, 0.15 dot 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 times x, or this is going to be plus x, times x, divided by 6.23 times 10 to the minus 8 minus x. So when I'm thinking about the simplifying assumption here, the SA, x relative to 0.15, I would say it's good. X should be small relative to 0.15, but will x be small compared to 6.23 times 10 to the minus 8? I would worry about that. And so what I mean by advanced, I might just do this for the numerator. I might make the simplifying assumption for the top, or I might try for both. If I try for both, then I have to say that x is going to be much smaller than 6.23 times 10 to the minus 8 and see what happens. And so if I do that, then the x drops out of the binomial terms here. And we just get x. And then I calculate x here, see what that comes out to. So I'm going to get 2.2 times 10 to the minus 13 times 6.23 times 10 to the minus 8 divided by 0.15. Oh, maybe it's all right. I got 9.13 times 10 to the negative 20. Did it work? It appears to have worked, right? Because the percent change is going to be, okay, the percent change is going to be this. The change was 10 to the minus 20. The initial is 10 to the minus 8 times 10 squared. And so that's going to be 10 to the positive 12. I mean negative 12. 10 to the negative 12, 10 to the negative 10. So this is 10 to the negative 10%. And so it's good. So going back here, I'll just write this over again. .23 times 10 to the minus 8. I'm going to write both of these in terms of 10 to the minus 8. So in terms of 10 to the minus 8, I'm going to make this one bigger, so I need to make this one smaller. And so I'm going to make this one bigger by 12. And so I need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 9, 1, 3 times 10 to the minus 8. And so I'm going to get 6.23, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 1, 3 times 10 to the minus 8. So you can see we barely lost any of this. And then for the hydronium, I'm going to get 0.15. And how many zeros did I have up here? Oh, I don't have it. How many zeros did I have before 623? Four? Okay, thanks. Yeah, my word is gone. And so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 9, 1, 3. So did step 3, this is step 3, did step 3 add a significant amount of hydronium, and did it remove a significant amount of monohydrogen phosphate, because those can perturb step 2? And it's negligible, so step 2 should remain unperturbed. So stepwise continues to work. And then the phosphate's very small. The phosphate concentration is going to be at equilibrium 9.13 times 10 to the minus 20 molar. And so these are my equilibrium concentrations here. Finally, we have step 4. Step 4 will be what? Water. Just leave it there. Thank you. Okay, so we have the hydronium times the hydroxide, and basically I don't expect much additional hydronium here. The only reason we're doing this is to figure out how much hydroxide I'm going to generate. So I'm going to carry down the hydronium here. And then I'm going to ignore the liquids here. Those aren't going to change. So I'm going to make my ice table just over here on the right side. This H2O is a pure liquid. And so I'm going to get 0.15 dot dot dot, and then I'm going to get 0 molar for the hydroxide. And then this is going to be plus X molar plus X molar. And then this is going to be 0.15 dot 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 plus X times X. Because of the common ion effect, we have a lot of hydronium here to begin with. I expect the simplifying assumption to work quite well. And so this is going to be 0.15 dot 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 plus X times X. And then we're going to go ahead and apply the simplifying assumption here, SA. And that's just going to go 0.15 dot 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 times X, and then solve for X. And so X is, we know what KW is. KW is 1.0 times 10 to the minus 14 at 25 degrees C. 1.0 times 10 to the negative 14. And so I'll go 1 times 10 to the negative 14 divided by 0.15. 15000062300. Actually, my calculator can't hold that many digits, right? My calculator, although I don't know how many digits the iPhone carries. Do you know? Maybe 100. Maybe it's a lot more powerful. 9 zeros. I'm going to add these 4, 5, 6, 7, 8, 9, and then go 913. So I'm carrying that whole number there. See if it works. Equals. And so I'm going to get 6.6, 666 times 10 to the minus 14. There's actually 4 sixes that go after this. And then it changes, so it's not repeating 6. Was it a significant addition of hydronium? No. And so basically here, you know, we're going to end up with 0.15 dot 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 molar. I mean, all those aren't really going to change the pH. But what did change is the hydroxide. The hydroxide was a significant addition. I'm not allowed this many sig figs, but I'll just carry it. I'll round it at the end. And so that's step 4. Do we have to go to step 5? You know, phosphate is a moderate base. Because monohydrogen phosphate is a super weak acid. If monohydrogen phosphate is a super weak acid, its conjugate its conjugate base is moderately strong. And so this is a moderately strong base. In fact, this base is almost a strong base. What's at the border between weak bases and strong bases? That chart's wrong, by the way. Phosphate is right at the edge of being a strong base. This is moderate, borderline strong base. So do I have to worry? You know, phosphate is what we call a tribasic base. And what tribasic bases can do is they can hydrolyze water, and we do it in one step at a time. So here we have this. We're going to have monohydrogen phosphate and hydroxide. So do I have to worry about the hydroxide addition here now? I did all the hydroniums. So for the acid, we looked at all the hydronium ion contributors, but now I recognize that I have moderately strong base present, phosphate. Do I have to do Kb for phosphate? Now, Kb for phosphate is equal to Kb1 for phosphate, which is equal to Kw divided by the Ka for its conjugate acid. The conjugate acid of phosphate is monohydrogen phosphate. This is going to be the biggest hydroxide contributor. Now, my question is, do I need to do step 5? What do you think? I mean, phosphate is pretty borderline strong. What do you think? Should I do step 5 and figure out how much hydroxide I get from phosphate?
No.
The no? Okay. That's the correct answer. Is it necessary? No. Now, what is the reason why it's not necessary?
So we have like 9 times 10 to the negative 20 of phosphate.
Okay. No, because the concentration of phosphate is so small, we could ignore it. Is that what? That's not the answer that I'm looking for here. It's not because the concentration is small. We deal with small concentrations, and we can deal with those in Chem 1B, right? The answer is no, because we already did it. But you think, how did we already do it? We already did it. The way you can recognize that we already did it is this. This describes the equilibrium between phosphate and monohydrogen phosphate in terms of pOH. In terms of pOH. We already did it in step 3. If we go back to step 3, step 3 describes the equilibrium. Oops. Step 3 describes the equilibrium between monohydrogen phosphate and phosphate, but not in terms of pOH. It describes it in terms of what? pH. The situation is, if the pH goes down, what happens to the pOH? It goes up. If the pOH goes up, the pH has to go down. They're tied together. pH and pOH are tied together by Kw. And so we'd get this exact same answer as we had before. So we already did this equilibrium in terms of pH, not in terms of pOH. Does that make sense? So it would be redundant to do step 5. And that goes for every other base in there. Because phosphate's going to be the strongest base. Well, hydroxide's the strongest, but hydroxide is directly pOH. Then comes phosphate's the next strongest base. And then the next strongest base would be dihydrogen phosphate. And so we have bases in there, but all those equilibrium are already done. And so the same thing goes for dihydrogen phosphate. Let me see. Same for Kb, for, Kb for monohydrogen phosphate, first, which is going to equal Kb2 for phosphate. And Kb for dihydrogen phosphate. which is Kb3 for phosphate. So when would we do these Kbs? When we do these Kbs is if it's a base solution. We do these Kbs here in the next example, but before I do that, let's complete this problem here. Completing a problem is we want the inventory. So I have a beaker here. This beaker is labeled 3.0 molar phosphoric acid. What's inside of it? This is what we call the stoichiometric concentration. What's inside of it is this. We're going to have 2.85 molar. Actually, let's write it. Let me write it differently. It doesn't matter. We're going to have 2.85 molar H3PO4, only 0.15 hydrolyzed. And then we're going to have 0.15 ... molar hydronium. And then we're going to have, let's go from highest concentration to lowest. I don't have the numbers there. I'll just say etc. We can fill in the numbers because the next species will be dihydrogen phosphate. Probably remember the number, but I don't want to think too much. Followed by monohydrogen phosphate, followed by phosphate, followed by hydroxide. There. And the pH we can calculate. The pH is just equal to the negative log of the hydronium total concentration. And then we would be done. This is the only reason we do all the steps. Otherwise, for pH, I'd probably do step 1. For pH, I'd do step 1 here, but if it were like sulfuric acid, I'd do 2 steps. So if I look at the next example here would be sulfuric acid. Sulfuric acid has a Ka1 of very large, and then Ka2. Ka2 is 0.15. Or 0.015, what does it say? 10 to the minus 2? 1.5 times 10 to the minus 2, so 0.015. Kw is 1.0 times 10 to the negative 14. So if I want the inventory, I do all steps. Inventory and pH, do all steps. However, if I want pH only, do I have to do all the steps? No. Would you do Kw? No. Would you do Ka2? Yeah, this is a special case. When we have a Ka2, pH only, we're going to do Ka1 and Ka2. The reason we're going to do Ka2 is 10 to the minus 2 is considered big. Big enough to contribute. And so we get like an additional like 10% hydronium from Ka2, whereas up here in phosphoric acid, it isn't considered big. 10 to the minus 8 is considered small. So I wouldn't even bother with Ka2. If you're ever uncertain, just do it and see, you know. But we can use shortcuts like this once we have enough experience. Now, when would we do all those KBs? So I'm not quite finished here. So the next example, let's look at sodium phosphate. So the general rule goes like this. This is how you can remember this. For acids, this isn't looking so great. Only hydronium contributors are calculated. If you do hydroxide, then you're going in circles. You're in a mini Chem 1B death loop. Not a simultaneous death loop, but another one. You're just going in circles, wasting time. For bases, now sodium phosphate's a base solution. For bases, we do only hydroxide contributors. So if you start doing acid contributors in a base, you're going in circles. So we're going to go with 0.1 molar sodium phosphate. Sodium phosphate, step one is sodium phosphate's a strong electrolyte. So strong electrolytes are going to ionize. So we'll get 3 sodiums plus a phosphate. And so we start off with 0.100. And what's K for this? K for this is very large. You know, soluble salts, sodium salts, very large. So that means it's going to go to completion. So this is going to be 0.3 molar, and the phosphate will be 0.1 molar, because we got to follow the stoichiometry here. And so this solution is going to end up with 0.3 molar sodium ions. And then phosphate's a strong or moderately strong base. It's still considered a weak base, but it's on the stronger end of the spectrum. So we're going to go with phosphate plus water here. And that's going to yield monohydrogen phosphate and hydroxide. And then we'll calculate our Kb value for this. The Kb is going to equal Kw over Ka for what acid? The conjugate acid, which is HPO4, 2 minus. And so Kw is 1.0 times 10 to the negative 14. Ka for monohydrogen phosphate is 2.2 times 10 to the minus 13. And so what does that give us here? 1 times 10 to the minus 14 divided by 2.2 times 10 to the minus 13. 0.045. 4545. I'll just carry extra digits until the end. I'll round it at the end. And so the initial here, we'll just take this down here. The initial phosphate is going to be 0.1 molar. Water is pure liquid. 0 molar, 0 molar. And assume nothing's ionized. Minus X, plus X, plus X. And so at equilibrium, I'm going to have 0.1 minus X molar, X molar, and X molar here. And so this is going to be equal to X squared over 0.1 minus X. Now this K is kind of big, so the change might be significant, but I'm not going to worry about it and debate it. I'm just going to go ahead and apply it, the simplifying assumption. This is going to be X squared over 0.1, and so therefore X is equal to Kb times 0.1, and then take the square root of that. And so I get X is equal to 0.067, which is 67% change. So it failed. So I have to use the quadratic here. So using the quadratic, I'm going to get X squared plus 0.04545x minus 2.2 times 10 to the minus 14 is equal to 0. And I'll solve. What time do we end at? 55? 11? Okay. So I'll do this in the quadratic solver here. 0.04545, and that negative 2.2 times 10 to the negative 14, 2.2 e to the minus 14. Calculate, and I get an X is equal to 4.84 times 10 to the minus 13. So I'm doing quadratic now. Should have done it in a different color. Let's see if this works. I could carry more digits if necessary, but just go with this. .11 nines, 0.011 nines, and 5.16. Okay, and so we're going to double check our K value. So I'm going to get 484 times 10 to the negative 13 squared. Divided by 0.099. They say 11 nines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 516. .342 times 10 to the minus 24. If I look at that K value and I compare it to the K value here, it's way off. Do you see that? It's way off. So that tells me I made an error somewhere. And so I need to go back and correct my error. This is why it's important to always double check your K value. I noticed a lot of people didn't double check their K values. It could save you some trouble. So I'm going to stop here. Let me hand back your exam